In this video, I want to discuss some trends with respect to what sort of growth a particular piece of code may give you. So we'll do some different examples here, and then later on we'll do some take a look at some more kind of detailed or complete pieces of code and analyze them to figure out what their growth function looks like. But for now, this is kind of just an overview of the trends we typically see. So the first thing we might see is something like a assignment. So this is a constant time operation. Right? There's no dependency on this line here, right? A equal B plus C with any sort of input size. It's just something that happens, right? We're just adding two numbers and storing the result. This will take a constant amount of time. It's not dependent on anything. So this is very common. Any lines of code in your program that basically don't have any special flow control like loops or ifs, they're going to be constant time, right? They just happen. Second thing, you may have programs, right, that have code that has a logarithmic behavior. And that's actually, if you think back to when we talked about binary search actually is an algorithm, right, that happens in linear time because it has this property where it basically divides the search space in half every time it runs, and it narrows down where exactly the end result should be. So this here, right, it says, see page 47, you can kind of ignore it. That's actually in the slides, so just use that as a reference. So that particular code, well, it has a while loop, it has some ifs. Usually what happens is the code that looks logarithmic has some sort of a division operation in there. So instead of it being like a for loop that goes from 1 to n, plus plus every time, right, to move up one by one, usually logarithmic stuff has a division, right? We start at n, then divide it by 2, and then divide by 2 again, divide by 2, divide by 2 again, like that binary search, right? Narrowing down the search space by halving it each time. That's the type of thing that typically has a logarithmic running time, right, or logarithmic growth function associated with it. Okay, so that's one thing we see. And we see that in binary search. I already talked about constant time. Next thing is linear time. And let me actually kind of mark in here, right? It's not very straight, but okay. This is going from this is going from fast to slow. Fast. So ignore that stuff there. And then it goes down here to slow. Okay, so logarithmic time, right, is a little bit slower than constant time, or it takes a little bit longer, right? In constant time, there's no impact, there's no correlation, right, between input size and how long it takes. Logarithmic time, all of a sudden we have code that's logarithmically dependent on input size, right? It will get slower to run this thing as my input increases. So next thing I have, right, is linear. So linear is going to look something just like n, right? Linear is typically a loop. So here we have a loop. This is on I, right? And basically we're going from 1 to n, right? So I equal 1, my ending condition is I less than n. So from I to n. Actually, this loop, right, will run I minus 1 number of times. But it still looks like n, right? It still looks linear. Although if we're being exact with the growth function, then we should be writing n minus 1. So typically, when you see for loops, they're going to look like this, right? They're going to look like a kind of a factor of n. You generally will have to look at the starting point and ending point to figure out exactly how many times it runs itself. But in general, it'll look like n, plus or minus a little bit of stuff. Same thing, right, applies to like for loops, right? For loops while loops, right? Where while loops, maybe you have still an iterator variable, right? An I or an X, right? And you're doing plus plus on it each time. Again, that's going to be something that looks like an I. In general, it looks like n. In general, anytime you have a looping structure that touches all the numbers from 0 up until n, will look like n, right? So it doesn't really matter if it's a for loop, a while loop, or a while loop, a bottom checking while loop. It doesn't really matter. As long as it's touching that number of elements, then it'll be the same. It'll all look like n. Okay. So n log n, we haven't really talked about anything that has n log n performance. This was something we have in something like merge sort. So depending on what prereq you took, you may or may not have seen merge sort. Merge sort is a recursive algorithm for sorting an array. The mechanism of that algorithm is basically to divide it in half and then sort each side. And that log part of that trend, right, to say that this is linear arithmetic time, right? It's basically it's n and then log n. The log n comes from the fact that the algorithm is dividing things in half, right? It takes the input array, splits it in half, sorts each side. That split, right, is what gives you kind of the flavor of a logarithm, that log n. And then each side needs to be sorted, and to sort each side, you basically need to touch every element. Merge sort, I mean, it's a little bit more complicated, and it's worth talking about later on. But then when we have to basically sort those sides that have been split, we have to touch every element in there. That gives us something that looks like a factor of n, because I need to go and look at everything that's inside of there. N log n algorithms are kind of hard to analyze. I don't think you'll really see code that's n log n. Although maybe I'll do an example just so we can, later on, do an example just so we can see code looks like it, although it's something that can be hard to analyze. Next thing, quadratic. So what happens here for quadratic and then also cubic is that we end up with stuff that is basically just more loops. So we added here a new loop there compared to our linear. Here we added 2 loops. And so here, right, all we're doing is we're taking code that we're taking something that's already happening, right? A loop containing an if statement, and I'm wrapping another loop and then another loop. Every time I wrap in a loop, what happens is that I'm basically paying the cost, right, in my program of running this thing, as many more times. So over here, the loop that I've added goes from 0 to n. Well, that means it's happening n more times, right? So n times whatever's inside is n, so n squared. In general, there's a rule where we say, okay, I multiply these together, right? However many times the outer loop runs, I multiply it by how many times the inner loop runs, and that gives me how many times the stuff inside those 2 loops will run itself. So, that's just kind of a general rule, right? Whenever we have nested loops, we do something like that. Same thing happens over here, right? We would basically look at these 3 loops for the cubic, 3 loops for cubic, right? Multiply them all together, and that'll give us our n cubed. So in general, right, when we have loops, every time they get nested, basically we're increasing the power a little bit, right? So 1 loop is n, 2 loops is n squared, 3 loops is n to the third, 4 loops is n to the fourth. That just comes from just imagining that each of those loops happens n times, and if we want to represent that they're inside one another, we should multiply them together to represent this happens this number of times, and then for every time something outside happens, right, the other loop happens, the inner stuff happens again. So we do a multiplication there. All right. Here we have some kind of example programs here. Let me actually talk about those for a second. So for quadratic, an example of something program that's quadratic is check all pairs. So maybe this is the case where we want to have basically an input, right? We want to see maybe there's a duplicate or where they sum to something specifically. Whenever I basically need to look at a list of n elements, right, and compare it to every other n element, I have something like this. Check all triples. That's actually going to go to another program we're talking about called 3sum, which is basically going to look at an input set of data, pick all the triples in there that sum to 0, right, and check to see how many there are. So, and that's another example. The last thing in here, and this is a bit above us, is things that look like 2 to the n, or exponential time algorithms. So exponential time algorithms are special in that they have very little value to us. In general, an exponential algorithm is an algorithm that has a growth function that grows so fast that we cannot hope to be around for the completion of any program that uses that algorithm. So most of the things up here are polynomial. Well, actually, they all are, right? So these are all polynomial class growth functions. Polynomial generally means that if we have a reasonable size of input, we can put it into that growth function. Growth function says, okay, you can take this many operations, and that number of operations will be something that's okay for us, right? It will only take minutes or days or years or months or centuries, not too long. For a exponential time algorithm, it's not the case. Exponential time algorithms tend to take much longer, right? So they may tend to take trillions of years, right? Or usually what happens is it's like however long it takes to run this algorithm, it's like more. It's a longer amount of time than what we expect the universe to be around for. So it's not really useful for us. So unfortunately, there are several algorithms out there that are exponential time, right? That have code that looks like exponential, but basically they're worthless to us because we won't be around to see the result. They're just kind of we could build this thing, but we can't actually run it. So a little bit strange, and maybe something worth talking about later. All right, so that's kind of an overview of some general trends in code and what sort of growth functions they may have, what kind of complexity class we may have. And then later on, right, we'll go in and do some more examples looking at code and actually deriving growth functions for them.